Right now, somewhere on this planet, sunlight is hitting a piece of glass and rock and turning directly into electricity. No moving parts, no fire, no explosion, nothing spinning.
And here's the part that should bother you. That process, the thing powering entire cities, is quantum physics, happening on your roof.
Not science-y sounding quantum physics. Actual, literal quantum mechanics. The same field that makes physicists dizzy is bolted to your neighbor's house, and nobody's told you.
In the next few minutes, we're going to break open a solar panel. Not with a screwdriver, with your understanding, and show you exactly what happens in the 0.000001 seconds after sunlight touches silicon.
You'll see why solar panels don't work the way 90% of people think they do. Why they get weaker in extreme heat? Yes, really. And the one design trick that took solar power from science fair project to cheaper than coal. By the end, you'll never look at a rooftop panel or the sun the same way again. This isn't a theory. The core discovery behind all of this, the photoelectric effect, is what actually won Albert Einstein his Nobel Prize. Not relativity. This. Here's a question that sounds stupid, but isn't. What actually is sunlight, physically, when it lands on your skin? In 1905, Einstein looked at an experiment that had baffled scientists for years.
Shine light on certain metals and electrons pop off. But here's the weird part. Turn up the brightness of dim red light and nothing happens. No electrons escape, no matter how bright you make it. But switch to a dimmer blue light and suddenly electrons fly off immediately.
That made no sense under the old model, where light was just a wave. Waves should transfer more energy the brighter they get, period. Einstein's answer broke physics wide open. Light isn't a wave. It's a stream of bullets, tiny energy packets called photons. And each color of light carries a fixed, non-negotiable amount of energy. Blue photons hit hard. Red photons hit soft, no matter how many of them you throw.
This is the entire secret of a solar panel. Silicon atoms inside the panel are sitting there with electrons loosely held in place. When a photon slams into one with enough energy, it physically knocks that electron free, like a cue ball breaking a rack. That freed electron is a live, physical unit of electricity now wandering loose inside the panel.
But one loose electron bouncing randomly inside a slab of silicon does absolutely nothing for you. You need billions of them to move in the same direction at the same time, and that requires the panel to cheat. So how do you force a trillion randomly freed electrons to march in one direction, on command, forever?
Engineers took a slab of silicon and did something sneaky to it. They took the top layer and injected it with phosphorus atoms, which have one extra electron than silicon needs. Then they took the bottom layer and injected it with boron, which has one electron too few.
Top layer, too many electrons, all dressed up with nowhere to go. Bottom layer, electron vacancies, desperate to fill up. Where these two layers meet is called the p-n junction, and it acts like a one-way turnstile. Electrons can drift across it in one direction, but the door slams shut if they try to come back the wrong way. So now, when a photon knocks an electron loose, it's not just wandering aimlessly. It's standing at the top of a hill that's been deliberately tilted. It has nowhere to go but downhill, through the one-way turnstile, out through a metal wire, through your inverter, into your wall socket, powering your coffee maker, and back around to the other side of the panel to start again. That's the electric current. That's the whole trick. You're not creating electricity from nothing. You're building a rigged racetrack and letting sunlight fire the starting gun. Over and over,
millions of times a second. Which raises an uncomfortable question. If hotter days mean more sunlight, shouldn't panels produce more power on a scorching afternoon?
The answer is going to surprise you, and it's the reason solar installers actually prefer cold, sunny climates over hot, sunny ones. Quick myth to kill: more heat does not mean more electricity. It's almost the opposite. Think of the silicon atoms as a crowd of people standing calmly in neat rows. When a photon hits, it's like tapping one person on the shoulder. Clean, precise, easy to track which direction they now move.
But heat doesn't work like sunlight. Heat makes every atom in that crowd jitter and vibrate randomly. The whole crowd is now shuffling around, bumping into each other, out of formation. When your panel gets hot, that background vibration interferes with the clean, one-way flow of electrons through the p-n junction. Some electrons that got knocked loose collide with vibrating atoms and lose their momentum before they can escape through the turnstile. They just fall back and recombine, wasted. This is measured with something called the temperature coefficient, and most panels lose about 0.3 to 0.5% of their efficiency for every degree Celsius above 25 degrees Celsius. On a blistering 45 degrees Celsius rooftop, a panel can be operating at 6 to 10% less efficiency than its rated spec, even in blazing sunlight. This is why the best solar regions on Earth aren't necessarily the hottest. They're the sunniest and coolest, like high-altitude deserts. It's also why good installers leave an air gap under panels for cooling, and why panel efficiency ratings are always tested at a controlled 25 degrees Celsius in a lab, not in real rooftop conditions. Now here's where this gets uncomfortable. We've talked about the elegant physics, but there's a side to the solar industry that most explainer videos conveniently skip, because it complicates the clean energy hero narrative. Here's the part that doesn't make it into the glossy brochures. Making the ultra-pure silicon that goes into these panels requires heating raw quartz to over 2,000 degrees Celsius in a furnace. A process so energy-intensive that manufacturing a single solar panel can take, depending on the factory's power source, more energy than that panel will generate in its first year of use. And a huge share of the world's solar-grade polysilicon is refined using coal-powered electricity in specific manufacturing regions, meaning some green panels are ironically born from fossil fuels. It typically takes a panel 1 to 4 years just to pay back the carbon cost of making it, before it starts being a net environmental positive. This doesn't mean solar is a scam. Over a 25-year lifespan, the math still overwhelmingly favors solar. But the elegant quantum physics we just described has an ugly, energy-hungry industrial process hiding behind it. The clean sci-fi story and the dirty factory floor are the same product. So if you take one thing from this video, it's this. A solar panel isn't collecting sunlight like a bucket collects rain. It's a rigged, one-way electron racetrack that sunlight forces open millions of times per second. And it works slightly worse, not better, the hotter it gets. Next time you see a panel on a roof, you're not looking at a passive object. You're looking at Einstein's Nobel Prize, still running, right now in real time. But knowing how the electrons get freed is only half the story, because that raw electricity coming off the panel is completely useless to your house in its current form. It's the wrong type entirely, and there's a device sitting quietly in every solar setup doing an even stranger conversion trick to make it usable. That's exactly what we break down in this video right here.